Hello viewers, this is Dr. Aisha Nazov with my next lecture in the econometrics series. In my last lecture, I was covering about the concepts of two-stage least square that I'm going to continue in this lecture as well. So if you want to understand, this lecture content efficiently, I would highly recommend that you watch the previous video that I'll share in a. Okay, so I would like to request that before watching today's video, you watch this video so you'll better understand things in continuity. If you haven't done that, go to the channel Hub, right? And this is the channel name, Hub. So if you go to the Hub channel, or you simply note this URL, and this is the title of the lecture I'm talking about, Threats to Internal Validity and Introduction to IV Regression or Instrumental Variable Regression, Use of Two-Stage Least Square. So this is the complete video title. If you type Hub and this complete video title, I'm sure you'll be forwarded to this video which I'm talking about. Okay, so once you watch this video, you will understand today's lecture much efficiently. Okay, so by the way, this particular page which is right in front of you is actually the last page or the last view of the video I was talking about. So this is just a recap that the beta estimator in the two-stage least square is an unbiased estimator. It is unbiased and it is normally distributed. So we will start the discussion from this notion of normal distribution for the beta estimator under TSLS or two-stage least square. Okay, so let's discuss the topic of normality of beta 1 hat TSLS. Okay, so if you have a little bit of a background in statistics, and if you don't, I think it's quite challenging to understand the concepts of econometrics. But so if you're challenging yourself and trying to straight jump or dive into the ocean of econometrics, it's better that you learn some of the related terminologies. So we have a theorem in statistics which is called central limit theorem. Okay, so what is this central limit theorem? It implies that no matter what is the probability distribution of x, that is, no matter what is the data generating pattern of a random variable x, the probability distribution of x bar is normal. It is normally distributed. In other words, what is a normal distribution? It is actually a bell-shaped distribution. Okay, so if you are studying this particular lecture, it's better to go and revise your concepts or learn your concepts related to central limit theorem. What is a probability distribution? What is a normal distribution? So that you can better understand the terminology that is being heavily loaded into today's lecture. Okay, so what I was saying, that central limit theorem states that no matter what is the probability distribution of the random variable x, the probability distribution of the mean x bar is normal. Now what does that mean? It actually means that, for example, if the random variable are stock returns, so no matter how the stock returns are behaving in their actual form, if we take the average returns, right? And what do we mean by average return? That is, if we consider that we are doing repeated sampling, that is, we are analyzing sample of stocks in different random samples. What I'm saying, I'm analyzing series of stocks, right? For example, series of 30 stocks, or you could have a series of 500 stocks, depends how much is the sample size. So if you have a series of stocks and you don't know what is the pattern or the distribution of stock returns, but the distribution of the mean returns, arithmetic mean of return, that is x bar, will be normal with mean equal to expected value of x bar and variance equal to sigma square over n. So now what is this expected value of x bar? I would strongly recommend that you better go and learn the concept of sampling distribution of a statistic. For now, I will try to make you understand this technical concept in a much easier manner. So expected value of x bar is actually the average of averages. Like, what is x bar? It is actually average of stock return series. So for example, if in repeated sampling I have 100 such series, so I will have 100 values of x bar, and average of those 100 x bar, that is average of average stock returns, will be equal to the population average. That is, it will be equal to the average return had we analyzed the complete data of stocks, right? So I'll pause a lecture here for a. Okay, so the probability distribution of x bar is normal with mean equal to expected value of x bar and variance equal to sigma square over n. And what is this sigma square? It is the variance of x, like in this example, variance of stock returns if we have access to complete population data. But generally we don't have complete population data, and that is why we are relying on a random sample, right? Okay, so if we are relying on a random sample, we can substitute this sigma square by sample variance safely in large sample, because large samples generally are a very good approximation of the actual population. So that's why in large sample I can substitute sigma square by s square, that is the sample variance, which is equal to this formula that you must have learned earlier on, that is each value of x minus its mean whole square over n minus 1. So if you, those of viewers who are like this concept, like the sample variance is new to them, it's strongly advised that you go and explore the other playlist on this channel, which is statistics or the introduction to statistics playlist. Let me show you here as well. So I was talking about this playlist. Statistics lecture is the name of this playlist. If you go here in this playlist, you will see many lectures on basic statistics. For example, this one is on geometric mean. We have another one on mode. And similarly, we have this one, quantiles and measure of variation. Actually, this lecture has details about the concept of variance. So if you want to revise the concept of the sample variance, you can watch this particular video, right? Quantiles and measure of variation, lecture for 6th April. If you watch this one, you will understand what is sample variance. Okay, so coming back to the central limit theorem, it states that whatever the distribution of x, the distribution of x bar is normal with mean expected value of x bar and variance equal to this, where you can replace sigma square by the sample variance, right? Okay, so x bar follows normal distribution with mean mu. This mu is simply the population mean, which is equal to expected value of x bar, right? That if you don't have the actual population mean, if you take the average of all averages, you will find the value of mu. So x bar follows normal distribution with mean mu and variance s square over n, right? Okay. So what does that mean? In repeated sampling, if we do repeated sampling, in practice we generally don't. So central limit theorem, keep in mind, is a theoretical concept, because practically we always rely on one random sample. So theoretically, if we do repeated sampling, then x bar, that is the sample mean, converges to mu, or the population mean. So if we apply the central limit theorem to the two-stage least square estimator, which you can recall that one of the formula equation was that it is equal to covariance between z and y divided by covariance between z and x. And what is z? That is your instrument, x is your endogenous regressor, and y is your dependent variable, right? Z is the instrumental variable, Y is the dependent variable, and X is the endogenous independent variable, right? So this covariance is nothing but just an average of the cross product term. What is covariance, right? This is simply if you take average out this cross product term. So if you have to similarly covariance of Z and X will another average of the cross product term. So these are averages, right? So beta 1 two-stage least square in large sample follows normal distribution with mean beta 1 and variance equal to this expression, where this expression or sigma square is given by this formula, right, which we covered in the last video lecture as well, that I refer to right in the beginning of the video. Okay, so what we have just established that beta 1 two-stage least square is normally distributed, right? So what's so important about knowing the distribution of this estimator is that I can develop the confidence interval, I can do the standard statistical testing if need be, that we will discuss in the coming examples as well. Okay, so next we have the general instrumental variable regression model, right? The general instrumental variable regression model has 4 types of variable. So just get yourself acquainted with the terminology. The dependent variable is generally called Y, the endogenous regressor denoted by X. That is, what is endogenous regressor? That is regressors that is correlated with the error term, right? And why generally it is the case? Because we have two directional relationship, Y as a function of regressor, but regression is a function of Y, which we generally discuss in a perfect classroom environment, that quantity demanded is a function of price. But what price is being charged is sometimes a function of what is the quantity demanded. So if you have endogenous regressor, let this be denoted by X, the exogenous regressor, that is not unproblematic regressor, that is it is uncorrelated with the error term, and we call it W. Okay, and then we have some multiple instrumental variables. So what are instrumental variables? If you can recall from the last lecture, that they are highly correlated with the exogenous regressor, but they are not correlated with the error term. That is why we call them instruments, because they serve as an instrument for a better regression. So for instrumental variable regression to be possible, there must be at least as many instrumental variables as the endogenous variable, right? What does that mean? If the problem of endogeneity is, let's say, in 2 variables, then you should have at least 2 instrumental variables. You can have more, but that's the minimum, right? Like if you have 3 endogenous variables, you must have a minimum of 3 instrumental variables, right? So now we have this terminology. Exactly identified model is the one when the number of instrument is equal to number of endogenous regressors, right? Or M is equal to K. Under-identified model is when number of instruments is less than number of the endogenous regressors, or M is less than K. So IV or the instrumental variable regression in this scenario is not allowed. Okay, it is allowed if they are equal, or if the number of instrument is greater than the number of endogenous regressors, and such a model is called over-identified model. Okay, so actually why we are like not allowing this one? Actually, what is an instrument? It is an approximation of the endogenous variable. So if the number of approximations are less than the actual variable, that means that is not a sensical regression, right? So that's what I have written here, that the instruments are actually approximation of the endogenous variable. So if the number of approximations of say 10 pieces of information, it should not be less than the number of pieces of actual information, right? Okay. Next we have a key term and concept. So the general instrumental variable regression is given by this equation. that is the dependent variable being regressed on the x, which are the endogenous regressor, and w, which are the exogenous regressors, right? Okay. Now we have another z, or the instrumental variable, that we will be introducing under the setup of two-stage least square, that will be followed here. Okay, so TSLS with a single endogenous regressor, that is, we have one endogenous variable. So when there is a single endogenous regressor and some additional included exogenous variable, the equation of interest is given by this, right? We have single endogenous regressor, that is this x, and these w's, these are exogenous variables, right? Okay, so the first stage regression of TSLS is to regress all the x's, the endogenous variable, that is one endogenous variable on the. So in the first stage regression, we regress the exogenous variable x on zi's and wi's, where wi's were the included exogenous variable and z's are the instrumental variable. Okay, so this equation 12.14, or the first stage regression, is sometimes called the reduced form equation for x, right? So that you know the terminology which is standard and used frequently in the textbooks. Okay, so in the first stage of TSLS, the unknown coefficients are estimated by OLS, and the predicted values from this regression are x1 hat, x2 hat, and so on. Like if you have single endogenous variable, of course you will only have one, that is x1 hat only. Then in the second stage of TSLS, this equation 12.13 is estimated by OLS, except that xi is replaced by its predicted value. Like instead of xi, I will store the predicted value from this first stage, right? So what happens, actually you don't have to perform all these steps, because the statistical software, they built in, run this first stage regression, so and the second stage regression as well. Okay, so the predicted values, they are replaced in this equation, and then the y is regressed on the predicted values of x from the first stage and the instrumental variable using OLS. And this is how we get the two-stage least square estimators, right? Okay, so what happens when we have multiple endogenous regressor? The algorithm or the process is similar, except that each endogenous regressor requires its own first stage regression, right? That is, in first step, if we have, for example, 3 endogenous variables, I will first run the first stage regression for the first one, that is x1 as a function of all these, then x2 as a function of all these, and then x3 as a function of all these, right? And the good part is you need to conceptually understand the process, so that whatever is being reported by the statistical software, you can interpret. Okay, so once you have the first stage x hat for all the endogenous variable, and then in the second stage you just replace the predicted x's instead of the actual x's, and that's how you will get the two-stage least square estimator in the presence of multiple endogenous variable, right? So this exactly is being mentioned here in bullet form. So you can just have a look at this. This is exactly the same process that I have just discussed. Okay. So now if we have to, whenever we run a model, you know, we have to comment on the goodness or the efficiency of that model. So the instrumental variable is, or the process of instrumental variable regression, banks on the efficiency of valid instruments. So how come we say that the instruments are valid? Okay, first of all, the instruments and the exogenous variables are not perfectly multicollinear, right? That is, there is no issue of perfect multicollinearity between the predicted values of the exogenous variable and the predicted value of the endogenous variable and the initial exogenous regressors. Okay, so if there is only one endogenous variable, then for the previous condition to hold, at least one z must have a non-zero coefficient. That is, there must be at least one instrumental variable that is statistically significant in the equation 12.13. So where is that equation 12.13? Let me just go to that, like this one. Okay, this is the equation 12.13. So that's what is being said over here. At least one instrumental variable should be statistically significant. That is, one of the z's must be statistically significant. Okay. So instrument exogeneity. The instruments are uncorrelated with the error term because this is the point of actually introducing the instrument, that they are controlling the problem of endogeneity. So they must control, I mean, for the purpose for which they are introduced, that must be met. That the correlation between the instrument and the residual term should be 0. Okay. Then next I will check for what is the rule for checking whether the instruments are weak or not. And what is meant by weak instrument? You know, what was the selection criteria for the instrument? That they are highly correlated with the initial exogenous regressor, but they are not correlated with the error term. So if the correlation is not high enough, like the correlation between the instruments and the initial exogenous variable, if it's not high enough, it will be portrayed by the first stage F statistic. So whenever I will show you shortly that whenever you run the instrumental variable regression in STATA or any statistical software, it reports the first stage regression as well if you click on particular links or the particular icons that I will be discussing shortly. So if you have the first stage regression, of course the F statistic will also be there. So just note the value of the F statistic. So if the first stage F statistic is less than 10, it means that the instruments are weak. And in the presence of weak instrument, the TSLS estimator will become biased and inconsistent, right? That's why it is written even in large sample, because inconsistency is a concept of large sample. So next we have a practical application of instrumental variable regression to the data for demand for cigarette. This data set has variables regarding the annual consumption of cigarettes in the 48 states for the year 1985 and 1995. Okay, so if you want me to email this data set to you, like the public that is viewing and getting benefit from this, they can simply send an email request and I will send the data there. For my students who are currently enrolled in the applied econometric course, this dataset has been uploaded both on the learning management system, that is the LMS, and the Microsoft team for the course. Right? The general audience can just write an email request and I will send this data. And I'll post my email ID in the comment section of this video. Okay, so the variables in the data that I have just discussed about the consumption of cigarette, the first variable or one of the variable is pack PC, which represents the demand for cigarette because it is actually packs of cigarettes sold divided by population. That's why we call it pack per capita. Then we have the income or the state personal income, right? As I said, this is state level data. So we have income for the ith state. Tax is the average state, federal and average local excise taxes for the fiscal year, and average PRS represents the price. It's the average price of cigarette during fiscal year, including sales taxes. And tax S is actually a cigarette specific tax, right? This is average excise tax for fiscal year, including sales tax, right? So and since this includes sales tax, So it will be levied on all the sales of the cigarette packets as well. Therefore, this represents cigarette-specific sales tax. Suppose we want to estimate the 10-year price elasticity. If those of the viewers who don't understand the concept of elasticity or price elasticity, I'd highly recommend get yourself acquainted with the concept of price elasticity so that you can understand the discussion that we are progressing with. Okay, so we want to estimate the 10-year price elasticity. We do this by considering quantity and price changes that occur over 10-year periods. So, I mean, it's up to us. If we have such type of a data that we want to analyze the changes over 5-year period, then we should have data for 5-year frequency. For now, I have data for 1995 and 1985. So that's a difference of 10 years. That's why I said that I want to analyze the elasticity over a period of 10 years. Okay. So if you know that if we have to measure elasticity, the OLS regression must be measured in logarithmic terms. That is, the dependent variable should also be in log, and the dependent variable, that is both dependent and independent variable, they should be expressed in log form. So this ln is actually natural log. So what I have taken, natural log of quantity of cigarettes sold in 1995 minus the natural log of the quantity of cigarettes sold in 1985. So that is actually differential in the quantity sold in logarithmic form, and let's say we call it QD, right? Then we have INC, which is the income differential across the 10-year time period. Similarly, we have PD over here, which is the price differential, that what was the price being charged in the ith state for the year 95 and then 1985. Okay, so if just a little bit of more clarity, if you want to, you just have a look at the data file that I was mentioning. So we have these like 48 states. Let me scroll down. So we have these 48 states of US, and the data we have for initially these are all 1995, and similarly we have the data for 1985 as well. So what I have done is I have actually copied all the 1985 series data right here, right? So, and then you can note that I've written POP2 or PACPC2. That simply means that's to differentiate from the actual variable name that were like PACPC is the quantity sold or the quantity demanded in 1995. PACPC2 is the quantity of cigarettes sold or demanded in 1985, right? So similarly, we have all the variables, and I have attached a to symbol here. Then I have this type of variable, PD. If you can recall from the notes, what is PD? PD is change in price, QD is the change in quantity, income D is the change in income. So what I have done is I have simply computed by using the generate command. PD is equal to like average price this one minus average price this one, like tick, right? So this is the price for 1995, and then we have the price for 1985. Okay, so that's how I've calculated PD, income D, tax D1, tax D2. This tax D1 is actually change in the tax. Let me tell you this particular tax, which was the like general tax. Tax D1 is change in this tax, and tax D2 is the change in cigarette specific tax, right? So that's how the data sheet is being constructed. Okay. So now what, coming back to the actual aim, like regressing. Okay, so the two instruments that we are using are the sales tax and the cigarette tax. And let me tell you what is being endogenous here, price. If you recall the standard debate of endogeneity in the price and demand debate, it says that quantity demanded is a function of price, but what price is being charged is sometimes a function of what is the quantity demanded. So we have an issue of endogeneity. So exogenous, or sorry, the instruments are those variables that are highly correlated with price. So you see sales tax and cigarette specific tax, they are highly correlated with the price. So we have also taken these in differential form, like tax D1 is the change in tax, general tax, and tax D2 is the change in the cigarette specific tax. Okay. So to ensure that the instruments are exogenous, we must minimize the issue of omitted variable bias. So if we regress quantity demanded on price, we are skipping an important variable present in the data set, that is state's income, right? So what is the price being set by the supplier also depends upon what is the general income pattern in that state, right? Accordingly, the supplier will decide that if it's a district earning higher, the price set will be set in a different manner. If it's a district whose income is low, so the you can say the purchasing power is low, and accordingly the price charge will be different. So we include state's income in our regression. Okay. So just before I run the actual model, if you just calculate the correlation between the demand in cigarette and income for the year 1985, the answer will be minus 0.334. And how can you do that? That's actually very simple. So you correlate PAC PC, right, with price, which was ABG PRS, right? You see, average price, AVG PRS. And I'm doing it for 1985 data, and this comes out to be minus 0.6291, right? So this value overwritten here is, I think this needs correction. This is not minus 0.334, it is minus 0.6291. So that means we have in correlation, negative correlation between what the price being charged and what is the quantity demanded. Similarly, you can check for the other year as well by using PAC PC2 and by using AVG PRS2, right? So I leave it to the viewer to try that correlation as well. Okay. So that means income is a significant predictor, or it is significantly related with the quantity demanded of cigarettes. So we must include this in the regression. So if we regress QD, that was the change in the quantity demanded on income D, and we declare PD as endogenous, right? That the price variable was endogenous, and tax D1 as instrument. So let's do that here. What's it saying is, if I go to STATA and I go to statistics and then endogenous covariates, single equation instrument of variable regression. So dependent variable is QD and independent variable is income D and endogenous is PD. So this is quantity demanded of cigarette, price charge for cigarette, and income, right? And the instrumental variable, as I said, first I have to introduce only tax D1. So okay. So it's highly recommended that if you tend to forget what's this QD, PD, income D, just watch the video from a little bit time earlier on, and you'll understand. So why this D symbol? It's actually just a difference, like the difference in the quantities across the 2 years, difference in the price across the 2 years, difference in the income across the 2 years. Okay. So endogenous covariates, single equation, income D, and then I will press OK. So these are the results that I have copied here, these coefficients and the p-values, right? Then I want to see the value of the first stage F statistic. As I just told you that you have to note if it is less than 10, that means that the instruments are weak. So how can I get this value in STATA? Okay, so once just right after running the model, go to post estimation and then reports and statistics and choose report first stage regression statistics and click OK. Right now you have the F value 89.4489. That is what is written here. So that means this instrument is not weak because this first stage F statistic is not less than 10. Similarly, if we follow the same procedure for cigarette specific tax, that is, this time we will treat tax D2 as an instrument. Then you get these results, and this is the value of first stage F. That you will follow the similar procedure that I have just followed for tax D1. Now if I introduce both type of taxes as instrument, right? I introduce tax D1 and tax D2. So let's see what happens. So endogenous covariates, this time I introduce tax D1 and tax D2. Right? So this time these are the coefficients that are written here, right? And the p-values. Now if I want to test the hypothesis whether all the instruments are they insignificantly related to the random error term. In other words, are the instruments really exogenous? All the instruments exogenous? Right? Because this was the sole purpose of introducing the instrumental variable. So if I have to test it, what I will do, I will store the predicted values from the last run instrumental variable regression. Right? I've just run the instrumental variable while I introduce, let me discuss once again that I just ran this regression. Why I introduced both tax D1 and tax D2 as instrumental variable. For now I press cancel because I've just run it, so I don't want to run it again. So I go to post estimation and I click on this prediction and residuals. So this way I can store the residual values and I can generate any variable name. For example, if I call it, let's say R. It's up to us, whatever name I can choose it, right? So now I will regress R on, just have a look once again, R on all the instrument and all the exogenous regressors. So I will regress R on tax D1, tax D2, and income D. That was the exogenous regressor. Okay. So you see, this is the value of F from this regression, 1.09. So note this value of F, 1.09, and okay. Now you calculate a statistic called the J statistic, which is equal to M times F. So value of F is 1.09, M is the number of instruments, so J stat comes out to be 2.18. So you reject H naught if J is greater than chi-square at 1 degrees of freedom at alpha. And why is this degrees of freedom 1? Because it is actually equal to number of instruments minus number of the exogenous regressors. So we have 2 instruments and 1 exogenous regressor, which was income D, right? So 2 minus 1 is 1. So we have reject H naught if J stat is greater than chi-square at 1 degrees of freedom at alpha level of significance. So if you use the chi-square table at alpha is equal to 0.05, the chi-square value is 3.84 and your computed J stat is 2.18. So 2.18 is not greater than 3.84. That means we fail to reject H naught and we conclude that both instruments are exogenous, right? So there is no need to drop any instrument from the model. Had this H naught been rejected, then we must think which instrument we should drop, and it's not a statistical inquiry. Then the question comes out to be theoretically which instrument is more strong. So you need to have theoretical justification which instrument to drop. Okay, then the final interpretation is if you just go on the model that we have just run, right? If when we use both type of taxes as instruments, so the coefficient of price is negative 1.28. So the purpose was to estimate the price elasticity. Okay, so the interpretation is if we increase the price of cigarette by 1%, quantity sold is expected to decrease by 1.28%, right? So that was one practical application of the instrumental variable regression, and it's strongly recommended that if you are a regular user of this channel and you are targeting or you're aiming to build on your expertise in statistics and econometrics, do subscribe to the channel and watch all the playlists. Shortly, I will also be uploading more videos on the use of Python and further topics on econometrics, right? So Dr. Aisha Nazuk here saying goodbye to all the viewers. Best of luck. Watch the video repeatedly and use the data set. I mean, make sure you understand the concepts. Thank you. Allah Hafiz.